This section of 9.2 is a continuation. We're going to now take the individual laws of pressure, volume, amount, and temperature and combine them into what we call the ideal gas law. And then we're going to do a bunch of problems where we use the ideal gas law to compute values for different various gas problems. If we take each of the individual gas laws developed by Boyles, Charles, Avogadro, and Gay-Lussac, we can combine them into one gas law that sort of covers it all. We call that the ideal gas law. So the relationship is pressure times volume of a gas equals the number of moles of a gas times some constant times temperature. This gas constant is the same for all gases, whether it is hydrogen gas, whether it is methane gas. We use the same gas law. And that constant is actually equal to 0.082058 liter atmospheres per K degree mole. Each of the quantities in the ideal gas law have units associated with them: pressure, volume, quantity, and temperature. We bring those all together in a single equation with a constant, which sort of unifies all those different units for those different variables. So the gas constant is the same for all gases, whether we have nitrogen gas, hydrogen gas, methane gas. However, it does depend on what units we use. So if we're measuring volume by liters and we use atmosphere for pressure, our gas constant is 0.082058 liter atmospheres per K, the temperature, per mole, the amount. And that is the most common being used today. However, if we measure pressure by using bars, the gas constant is different. If we measure pressure using torr, the gas constant is different. If we measure both the volume and the pressure using kilopascals or decimeters cubed, we have a different constant. And finally, we have a gas constant if we use joules per K per mole. Again, the most common one that we'll use is going to be the top one here, but we will have these available in case we need to convert units. A lot of these constants can actually be put together in a larger constant if we measure our volumes for, say, at a constant standard temperature and pressure. For example, the standard pressure is 273.15 K. Standard pressure is 1 atmosphere or 760 millimeters of mercury. We can conclude that at standard temperature and pressure, 1 mole of any gas has a volume of 22.42 liters. And that's just substituting these values in for the temperature and the pressure as stated here in the standard temperature and pressure. Let's now use the ideal gas law to work out some problems. So in example 9, what is the volume of 1 mole of gas at standard temperature and pressure? Well, I already know that, but let's calculate it out. So I can rearrange my ideal gas law to say the volume is equal to nRT over P. N is 1 mole. The gas constant is 0.082058 liter atmosphere per K mole. My temperature at standard temperature and pressures is going to be 273.15 K. And my standard pressure is 1 atmosphere. Do the mathematics, 22.414 liters. Example 2. The reaction used to deploy an automobile's airbag is actually a high temperature decomposition gas of this sodium azide, NaN3, and it produces N2 gas, and it produces it very rapidly. Here is the chemical reaction equation for that. I have 2 moles of sodium azide. It decomposes to form 2 moles of sodium and 3 moles of nitrogen gas. The question here in this example is, how many liters of N2 at 1.5 atmospheres and 30 degrees C are produced by the decomposition of 45 grams of sodium azide. The first thing I'm thinking about in this equation is I need to convert that 45 grams of sodium azide into moles because I want to know exactly how many molecules of sodium azide I'm starting off with. So we take my 45 grams of sodium azide, using the molecular weight of sodium azide, I can convert that to moles of sodium azide. But in this reaction, I'm now going to use that relationship in the chemical reaction here to find out how many moles of nitrogen gas I'm going to produce. So for every 2 moles of sodium azide, 2 moles, I'm going to produce 3 moles of nitrogen. So I literally calculate how many moles of nitrogen gas I actually produce when I start with 45 grams of sodium azide. Put it back now into my ideal gas law, 1.04 moles times the gas constant times the temperature in K, so I got to keep that in the right temperature range. That's going to be at 30 degrees C, divided by the pressure. I'm going to have 22.5 liters of gas produced. So that's a lot of gas produced, and it gets produced quickly. Example number 11. Gas occupies 400 milliliters at a pressure of 1 atmosphere. What will be the volume if the pressure is decreased to 0.750 atmospheres at a constant temperature? I know that the gas constant, I can rearrange that to set that my gas constant initially is equal to a constant, and after I change the pressure, I can actually set that up to the same constant. If I do that, I get my pressure initial times my volume initial divided by number of moles initial times my temperature initial is going to be equal to my final pressure times my final volume divided by the number of moles final times the temperature final. Well, we know several things are constant, right? I know that N and T are the same, so I don't change those. So they essentially cancel out of my equation. I end up with P1 times V1 equals P2 times V2. Oh, that's Boyle's law. So I can just plug into that. So I know my initial atmospheric pressure is going to be 1.0. I have a gas at 401 milliliters. I reduce the pressure to 0.750 atmospheres. Do the calculation. I get 535 milliliters. That's how much volume I'm going to take up if I hold the temperature and the number of moles constant in this reaction. Ideal gas law number 12. I have 1 liter of oxygen. It reacts with octane to form CO2 and liquid water. Well, that's just a combustion reaction, right? So I can actually write the balanced combustion reaction for that process. I have 2 moles of octane reacting with 25 moles of oxygen to give me 16 moles of CO2 and 18 moles of liquid water. The question here is what volume of CO2 will be produced at constant pressure and constant temperature if I have 1 liter of oxygen. Okay, so let's do the mathematics. My initial pressure, my initial volume, my initial amount, initial temperature, again, is going to be equal to a constant, so I can relate that to my final. I do a cancellation because I'm going to be working at constant pressure and constant temperature in this case. I'm not changing either of those. My ideal gas law relationship reduces just to Avogadro's law. So I have 1 liter, which is I'm going to have 25 moles. Where did I get that 25? Right off of the reaction equation here is going to be equal to the final volume times 16 moles. Do the arithmetic. My final volume is going to be 0.64 liters. Example 13. What volume will 2.6 moles of nitrogen occupy at 0.640 atmospheres and 31 degrees? Now, I'm not changing anything. I just want to solve the ideal gas law in this question here. So I can set that up, PV equals nRT. I want to solve for volume, so I rearrange it so volume equals nRT divided by pressure, and then I literally just need to plug in the values. I got 2.64 moles of nitrogen gas times the gas constant times the temperature in K. Notice here I've had to add 273.15 onto my 31 degrees C to get it into K, and divide that by the pressure. Solving the equation, this amount of gas will occupy 103 liters at this pressure and temperature. In ideal gas law example number 14, I'm going to start off with 100 grams of octane and I'm going to burn it. And I'm going to burn it at standard temperature and standard pressure, so I know those values. The question is what volume of O2 will be consumed? So I still have to write my balanced chemical reaction equation, 2 moles of octane plus 25 moles of oxygen gives me 16 moles of CO2 and 18 moles of water. I first want to calculate from the initial mass of my octane and my reaction equation what is the number of moles of oxygen that will be consumed. So I have 100 grams of octane divided by the molecular weight of octane, and then I can convert my moles of octane into moles of O2 using this relationship here from my directly off of my reaction equation. I get 10.93 moles of oxygen. Under standard temperature and pressure, I can directly go to the ideal gas law and solve for volume. So I take my ideal gas law, rearrange it slightly to solve for volume. I got 10.93 moles of oxygen times the ideal gas law constant times temperature in Kelvin, that's the temperature for standard temperature, and divided by my standard pressure. I solve that arithmetic and I get 244.8 liters of O2 gas that is consumed when I react it with 100 grams of octane. Example number 15 also involves a combustion reaction. In this case, I want to know the volume of O2, and I have specific conditions now for pressure and temperature at 752 torr and 25 degrees C, will react completely with 10 moles of octane. Here again is my reaction equation. I have my ideal gas law here. I want to solve for volume of O2. So the first thing I'm going to do is actually calculate how many moles of O2 I have, and I can do that by taking my 10 moles of octane, substituting in here from my reaction equation that for every 2 moles of octane I need to use 25 moles of O2. So if this reaction goes to completion and it's efficient, we'll have used 125 moles of O2 to react with my 10 moles of octane. I then also need to get all my temperatures into K, so I take my 25 degrees, I convert that to Kelvin by adding 25 to 373.15. I then plug everything back into my reaction equation. I got 125 moles times the gas constant. Oh, this one's different. That's because in this case, I'm actually working in torr this time rather than atmosphere, so I got to use the correct gas constant, which is 62.36 liter torr per K per mole, times the temperature in Kelvin, times the pressure in torr. That gives me 3,090 liters of oxygen. Here's another very interesting reaction. If I take potassium chlorate and I actually decompose it to form potassium chloride, I can actually generate 3 moles of oxygen. That's one of the experiments that the Mars rover is actually conducting. They're looking for this potassium chlorate because we can generate oxygen gas with it, which we can breathe, but we can also use it as a fuel to return spaceships back to Earth. The question here is, what volume of oxygen is produced when 5 grams of potassium chlorate reacts with the following reaction equation at standard temperatures and pressures. So if I have 5 grams of potassium chlorate, I can actually then calculate how many moles of oxygen are produced from this reaction equation. I first convert grams of potassium chlorate into moles of potassium chlorate using the molecular weight. I then convert moles of potassium chlorate into moles of oxygen using the reaction equation coefficients, and I get 0.061 moles of oxygen that are produced. And then we're working at standard temperatures and pressures, so in this case, I'm just going to combine all of my other standard temperatures into another constant, and I literally can say that the ideal gas constant times temperature divided by pressure is going to be 22.4 liters per mole. This is sort of a shortcut way of doing it, but you can still put in all the values here. Volume at standard temperature and pressure is going to be 0.061 moles of oxygen times 22.4 liters per mole, or 1.37 liters of oxygen. So you can see for every 5 grams of potassium chlorate on Mars, we can generate 1.37 liters of oxygen gas to breathe. Another reaction which is sort of related to space travel is reacting aluminum with HCl to produce aluminum 3 chloride and hydrogen gas. Hydrogen gas, when mixed with oxygen, can also burn and be used as a fuel. So let's sort of calculate how many moles of hydrogen gas I can produce here, because that's what the question's asking. What volume of hydrogen is produced when 9 grams of aluminum reacts with excess HCl, so I have more HCl than I need, making aluminum my limiting reagent, according to the final equation. And I'm going to do this again at standard temperature and pressures. So the first thing I need to know is I have 9 grams of aluminum. I know that. I want to calculate how many moles of actually hydrogen I generate. So I take 9 grams, divide it by the molecular weight of aluminum, convert moles of aluminum into moles of hydrogen based on the reaction equation here. I end up with 0.500 moles of hydrogen gas. I know at standard temperature and pressure, every mole of gas at standard temperature and pressure actually has a volume of 22.4 liters per mole. So I can just multiply those two values together. 0.500 moles times 22.4 liters per mole. I get 11.2 liters of hydrogen. And finally, I have example 18 where we use our ideal gas law equation. I have a 1 liter flask. It contains 1.13 grams of an unknown gas, and I measure the pressure. It turns out to be 0.850 atmospheres. And I measure the temperature, and the temperature of the gas is 20 degrees Celsius. Can we use this information to actually determine the molar mass of this gas, and then, in fact, determine what gas it is? What is this unknown gas? So I set up my ideal gas law where I'll solve for the number of moles. Because if I know the number of moles and I know the mass, so a moles, grams per mole, that's just going to be the molecular mass. So if I know the number of moles and I know the mass, I can actually solve for the molecular weight. So I measure my pressure. It's 0.850 atmospheres. It's all contained within 1 liter flask. I slide in my ideal gas constant, and I know the temperature, 273.2 plus 20 degrees. I can solve for the number of moles of that gas that are in my 1 liter flask. But I know the mass. So I know the mass and I know how many moles I have. I can actually solve now for grams per mole, which is just molecular weight. I go back to the periodic table, and lo and behold, oxygen, O2, has a molecular mass of 32 grams per mole, or 15.999 times 2.